There's been a few of you who've been sitting in the audience for the past few minutes listening to us ramble on for a couple of minutes, but I just want to welcome everybody to our 40th webinar. And I was actually thinking this morning as I was getting this run sheet together that it's crazy to think when we started doing these webinars 5 or 6 years ago in the depths of COVID, that we would still be continuing doing these today. And, you know, it's something that we are incredibly proud of at Sustainable Builders Alliance, that we are still around and still apparently relevant and sharing information that the broader audience and industry want to hear. Today, in my very humble opinion, we're joined by 3 absolute powerhouses when it comes to moisture management and also understanding the impacts of moisture and water on our buildings. For those who don't know me, my name is Hamish White and I'm one of the founding directors of Sustainable Builders Alliance, and I'm also the director of Sanctum Homes, and I'm going to be your host for the webinar today. In the spirit of reconciliation, we would like to acknowledge the traditional custodians of country throughout Australia and their connections to land, sea and community. We pay our respects to elders past, present and emerging, and extend our respects to all Aboriginal and Torres Strait Islander peoples today. And today I'm joining this webinar from Wurundjeri land, which is the land around Birrawong in Melbourne. Now, you're all here because we all know that water kills buildings. Now, I bang on about this a lot on my own social media page. And, you know, I've certainly been following Sean for a long time. And, you know, recently Clarence and I met down in Tassie. And, you know, I do genuinely believe that the 3 people we've got sitting here right now are experts when it comes to managing moisture, understanding what happens to our buildings when they do get wet, how to prevent them, what to do if we do have water damage. Our first guest is Dr. Mark Dewsbury, and Mark has been involved in the sustainable design of commercial and residential buildings in the public and private sector for more than 30 years. He is currently a senior lecturer and director of the Tasmania Architectural Science Laboratory within Architecture and Design at the University of Tasmania. His research focuses on methods to inform, design and improve the construction, durability, thermal performance and indoor environment quality within buildings. From 2002, his focus was on building envelope thermal performance. I'm just going to pause on that for a second because that is 20 plus years ago that Mark was researching a building envelope thermal performance. And it's almost become like a cool thing now, and which I think is pretty incredible. It's the fact that it's taken so long to get to where we are is pretty mind-blowing. Which in 2008 merged with moisture and mold design considerations. His research applies internationally accepted principles and World Health Organization recommendations to inform national regulatory development and building design and construction guidance. In 2024, he was made a Fellow of the International Architecture Science Association. Our next guest is Clarence Macalister from Ionic Construction. He's a scientist, a carpenter and licensed builder. Over 20 years in the industry. He's worked on a wide range of building defects and rectification. The majority of his time spent on the tools tackling problems from the normal to very unusual. He deals with many complex matters like condensation, energy efficiency, groundwater, salinity, waterproofing, etc. In particular, assessing and working out specific practical solutions. This involves a load of technical knowledge mixed with years of building site problem-solving experience. Since 2019, Clarence has been the Master Builder Tasmanian representative for all matters to do with condensation and mould. This has included developing and delivering training on condensation management with various industry experts. This training has been delivered to over 600 attendees. He is on the ABCB Technical Reference Group for condensation. And our last guest, who is probably one of the shyest ones sitting on the panel today, and he definitely doesn't have to, because you all know him and you all love him. He's Mr. Sean Buchanan. He's director of Haven Homes Tasmania and a carpenter with over 10 years experience. He's passionate about building resilient homes that stand the test of time, grounded in good building science and practical know-how. Sean is known for his down-to-earth approach and his focus on the on-site details and how they unfold during construction. He believes sustainability isn't just about energy efficiency, it's about durability, and he loves sharing that message with others in the industry. And if you don't follow his social media page, Tassie Builders blog, you should definitely go and check it out. Now, quite appropriately, today's webinar is brought to you by our longtime supporters, friends, and platinum sponsors, Performance Membranes. And according to their website, they do one thing and they do it well. They are Australia's only dedicated pro-climate distributor, exclusively selling pro-climate systems and accessories. Performance Membranes has everything you need for your build or renovation in weather-resistive barriers or WRB and intelligent air barrier systems and project-specific accessories. They also offer free technical install training either on-site or at their HQ in Knoxfield. And I do believe that PHCP also offers some training down there in Tassie through Justin and Mog. All right, a little bit of a disclaimer. Sorry, I know there's a lot to get through before we actually get to the good stuff, so I do apologise. All content provided by Sustainable Builders Alliance should be used as a general guidance and for reference purposes only. Always seek independent advice and, if required, verification, no matter the circumstances, including but not limited to instances where loss or damage may occur. No account has been made or has been or will be taken into consideration for specific circumstances. No content should be relied on in that way. Views and opinions are solely personal and that of the person at the time of publication and may not reflect the views and opinions of Sustainable Builders Alliance. Sustainable Builders Alliance makes every effort to ensure content is accurate at the time of release publication. Sustainable Builders Alliance accepts no responsibility for any content that may become inaccurate over time. All right, I got all that stuff out of the way, so let's get stuck into it. Today's format is going to be a roundtable discussion, and I've absolutely no doubt that we're not going to have enough time to get through all our questions, and I've no doubt with the brain power that's sitting in this room today that we could talk for hours on maybe just one question. So we're going to try and get through as much as possible. If you do have any questions, please pop them down in the chat below, and I'll be monitoring that and I'll try and feed them through as we go. I do have some questions we'll start off with, and I'll be jumping around between Sean, Clarence, and Mark. Now, to open this up, I'm going to start with Clarence. Clarence, why is this a problem? Why are the differences with modern building, and what are the differences between modern buildings compared to older buildings?
Look, I think the first one is the materials we're using. It might seem a really obvious one, and what I'll do, I'll just share some photos if I can. Where are we? Here we are. And so you think of years gone by, we would have used hardwood, and well, hardwood's probably the biggest one. And today we're using MDF, we're using radiata pine, we're using all these water sensitive materials. And I'm struggling to get this one up. Can we just can I do a screen share there? Is that possible to do?
Yeah.
Screen share, yeah. So this one here is a can we see that there? No, screen.
It's coming up now.
Coming there. And so this was a house which was clad in can you see that there?
Yep.
Yeah. So that's a house that was clad in Baltic pine, which is highly undurable radiata pine frame. So the first thing is the durability of the materials, and you think MDF, you can get an MDF exterior grade door made out of MDF. That's nuts. That's the sort of stuff we're dealing with. I'll stop sharing now. The other thing too is that the way we're building is very different, and I'll pull up this other slide here. Where are we? This one here, and this is one that Mark and I use in our training to get this concept through. And if we build a house like this these days, and this is more an issue about building physics than about materials. Can you see that one there of that flat roof house? Yep. And so if we build a house like this these days, and this, like I said, this is more to do with building physics than actual materials. Well, it's a bit to do with materials, but if we had this thing now, we've got a flat roof, we've got drainage issues, etc. But this thing would have been built in the 70s, 80s, 40 years later, it's still good as gold. But the difference is we have no roof insulation in a building like this because you've got no roof insulation in the older build. There's more heat drive through the building envelope, and as Joe Steinbrück says on you've probably heard him with Jessica Kismet, that we've got more drying potential because we've got the heat flow. The other thing is that the attic space at the top would not have been wrapped. It would have just been trim deck over the top. So we've got a lot of air naturally flowing through there. Again, more ability to dry. The hardwood is moderately durable. And we've got the space below would have been highly air leaky. So even when it was heated, you're not getting this sauna effect. So that they look the same, but 4 key differences can be the difference between significant durability and dreadful durability. And I'll just bring up one more here, which is this issue of actual construction practice. Now, I'll share this screen here, and it's a little bit small, but stop share. I'll pull up this one. And I think the other real big one is this issue of how we actually, our trade skills. Now you can see this one here. We've got a flashing, a ColourBond flashing that actually slopes back into the building. Ditto on the top one, and here the weather resistive barrier, even though it's a crappy one, doesn't go over the flashing. If I'd done this when I was apprentice 20 years ago, I'd have got my backside kicked. But this was from a multi-award winning builder. And this is par for the course, and they go, surprise, surprise, my building's leaking. So you combine those 3 things, the durability of materials, the changes in building physics, and poor trade skills. We've got a perfect storm.
I'm going to fast forward to now, and I'm probably going to throw this over to Sean. Sorry, mate, I'm going to throw you on the bus here a little bit. If you saw that design come to you right now with a flat roof, we've obviously got like somewhere between a 5 and a 2 degree pitch there. What are some of the considerations that you would, talk to the owners and the clients and the architects in pre-construction to try and manage the risk that you could play out in your mind if you don't take these steps? So what are some of the things that you would do if you saw that?
Yeah, that's actually funny that you bring that up, because a project that we just completed, we got in the ideal pre-con thing that's happening now. The contractors are involved early. That was the first thing we talked about with the designer. We're like, what's the pitch? And he's like, oh, it's this pitch. And we're like, nah, well, 10's cheaper. So if you make it 10, if you've got scope to increase the pitch, it's just a lot, like the products that we use, it's just a lot cheaper. The way that we detail it, it's a lot more cost effective than trying to detail a flat roof. So we always tell people, straight off the bat, it's cheaper to raise the roof pitch. That's not always architecturally possible. There's been a couple of designs where we've put that to them, and when you look at the design, you're like, yeah, well, you just can't get that to 10 because it's going to wreck the aesthetic of the building. And we just say that we have to detail it in a way that's quite different to what you may have seen before, because we don't want to put ourselves at risk, and we don't want to put you as a designer at risk for something that we know that's not going to hold up long term.
And what are some of the things that you would consider? Say, the architect and the owner were dead set on having a 2 degree pitch on that roof there. And what are some of the things that you would work through in design and then obviously execute that on site? What are some of the things that you would put into play there? I'm thinking condensation management internally. I'm thinking vapor control layers externally, etc.
Yeah. Well, we're used the Pro Climber stuff for a little while now. So we would just follow their spec. So if it was flat, we'd be putting sheathing on there. The internal air barrier, from my experience, that's the hardest thing to get through. People can digest some of the other stuff. That is one that can be challenging. But yeah, the sheathing, the increased weight to the trusses, the increased time to install the membrane, it's all adding costs. But that's where we start. The next one that we've got coming up, that's 2 degrees. They're trying to push it to 5, but we've just already given them straight off the bat the preliminary pricing of that roof is probably going to cost you an extra 60K to build.
Yeah. So, Mark, I might bring you into this conversation too, because one of the things I guess would love the listeners to understand is there's a couple of things at play there. We've obviously got our flat roof with water coming from the outside, and then we've got vapor drive from the inside, pushing up through the building, and it's obviously got to get somewhere. So what are some of the considerations if we're thinking about that flat roof setup? And Sean brought up, that Pro Climber system before, and there is actually a flat roof system that Pro Climber has brought into existence. So could you maybe explain some of the science or some of the physics that's happening there
Actually, and I think it's interesting because I'm remembering back to the 90s when I was a Institute Properties manager. I had 11 TAFE colleges in New South Wales, and a fair chunk of our budget was fixing low pitch roofs that were built in the 1970s. So in some respects, it's not a new problem. Flat roofs don't seem to aren't that durable for long-term situations. But yeah, so I guess there's a few things there, and it's a really good question. So, where do you start? I'm sure you could talk for 3 hours on one topic. So the first thing is
let's go from
yeah.
the
Well,
inside.
I'll go from
Let's go from the inside.
yeah. That's right. So the first thing is that we're making we're sitting around right now making about 80 grams of water vapor an hour each. So we're adding that. So no showers, no sinks, it's just us living. We're making 80 grams per person of water vapor per hour, and that's now inside the building. Now, sadly, we went through this fad of downlights for probably 20 years. So we had all these holes which allowed 1 litre of air per second to go between the living room and the roof space, and so that was actually taking that water vapor into the roof space. At the same time, we were doing increasingly airtight roof spaces, which is against practices going back to the Egyptian time. We've known that since Egyptian time we need to ventilate our roof spaces. So we were creating a situation where the vapor from us was going to the roof space and causing roofs to rot quite quickly. So that sort of highlights, if you think about the proclimate products or even before proclimate products, the first thing is how we're controlling vapor within the building. So whether that's an interior wall membrane or an interior ceiling membrane, how we're actually saying we're controlling where the vapor goes. And we put in management practices, whether it's material or ventilation it might be, to help manage that. So then we say we've now got a roof space zone where we're controlling how much vapor comes from the house into the roof space. But the roof space itself is a very dynamic zone in terms of, with night sky losses, you can have minus 12 degrees in a roof space down to the ceiling, which might be 21.1 degrees Celsius. And so the temperature range in there is phenomenal. And so whatever vapor is in there, whether it's come from outside or, up through water, it might be, it's reaching points where it wants to condense on things. And so the Americans have had problems for decades regarding sweating steel roofs because the moisture's there and it just forms on the steel and runs down the steel. The advantage we've had with timber structures, hardwood and softwood, is that the timber will absorb a bit of that. And so depending on the durability of the timber, how long that might last. And then sarking, as we've been adding different types of sarking products, and some of those have limited the capacity for the vapor to leave. Some have been in more recent products, they're vapor permeable. So thinking about even the Proclimate flat roof system, whether it's the vapor permeable product on the top, allowing for the vapor to still leave, but they've got ventilation above that. So recognizing we want to get the vapor to that ventilation zone between the roofing material and the sarking, and then promote that to leave. And I guess the draft 2025 code, which sadly is not going to see the light of day from what we can see at the moment, it was actually, we know that if I look at regulations from other countries, the magic number used to be 16 degrees, which was the roof is more than 16 degrees. What we call stack ventilation or chimney ventilation works brilliantly. Between 6 or 7 degrees-ish and that 16 degrees, it works about half as much. And so that's where we look at regulations we were doing in Australia and overseas, we're saying we need double the ventilation for that pitch. When you go even lower, we need to think about even more ventilation, which comes down to, well, how thick is the roof space? How thick is the ventilation space? The flat roof might not be as flat as it used to be to fit all these different things in.
When you talk about ventilation, we talk about ventilation, I guess, on the underside of the sheeting, the roof metal. Yeah. So what I'm hearing here is, like, on a flatter roof, we actually want a bigger cavity batten. So maybe 50, 70 mil or something like that.
Maybe 200 mils.
Yeah. Okay. Interesting. So I might bring Clarence into this conversation again. We talked about moisture moving up into that roof space, and this is probably not strictly to do with, flat roofs, but maybe just a normal, 20 odd degree roof cavity. And we've got all that moisture driving up through the building, and all that moisture is getting stuck because, for some, by chance, the roof has put on a really good membrane and the moisture can't get anywhere. what happens when that moisture or that timber is in that really humid and moist environment? What are some of the things that can happen within that roof space?
Yeah, look, I suppose there are two things. One is condensation, the other one is mold, and mold will occur at a lower humidity than what condensation will occur. So condensation by definition is where you have total saturation of the air, 100% humidity. But mold and that sort of problematic health scenarios can occur at far less than 100% relative humidity. And there's an article Mark and I did on LinkedIn a while back, and there's a thing, it's called a mold growth index, and it's on LinkedIn. I don't have it to pull up at short notice, but what happens is when you get the correct humidity and temperature conditions, mold will grow. If it's either too cold or too dry, mold won't grow. And and I think we're going to talk about this later, and I've actually got a whole bundle of them in roofs all around Launceston, is meters in the roof which actually have a mold index thing built into them. So, and coming back to what you mentioned before, from my analysis, and I'm up in roofs all the time, it would appear that hardwood has significantly more ability to deal with mold than what softwood does. So here we have things that appear the same, but if we have a hardwood that's getting into that danger zone more frequently, it will deal with it much better than the equivalent softwood. And the other thing is we're having all these micro changes in the way we build buildings. And one of the big ones that I've had a lot but been thinking about a lot lately is, you think of the membrane, and there's still a lot of buildings that can be built to meet the code with a membrane. So you've got a membrane, the metal roof sheeting, then a membrane, then your batten. But what used to happen historically is the sheets would all be 8-foot sheets, 2.4, 3 metre sheets, whatever. They'd have gaps everywhere. There was a drying path between the batten and the corrugates. That drying path between the batten and the corrugates no longer exists. So from my observations, that is the highest risk part of the building, the battens, because it's the coldest, it's where the moisture accumulates, and there's no drying path. And it's these very small differences that we're going to full length sheets with sarking that can make a huge difference. Then you put a bit of softwood in the mix and bam-o, you've got a big change. And that's not necessarily just with the flatter pitch roofs.
And is it something that, I guess that there's a reason why I've got the three of you here. We've got Sean building, new homes. We've got Mark with his 20, 30 plus, years of experience, like dealing in the condensation and moisture management space. And you're actually on the ground dealing with these old buildings in climate zone 7 in Tasmania, which you're obviously seeing a lot of this moisture in these buildings. What are some of the things that you've seen, and then how have you rectified them? Because we're obviously going to, we're coming into this time now where we're insulating, because that's what everyone's telling us to do. We're changing the physics of the building. This moisture's got nowhere to go now. Moisture's getting trapped in the building and creating this mold and rot issue in these roof spaces or in these walls. What are some of the things that we can do to slow down the process or eliminate the process when the problem is there? Or is there not a way to rectify it?
Yeah, look, I suppose part of it is a rectification thing that I see, and part of it is an early insurance policy, which Sean's probably in a better position to mention on the new builds. So I suppose that there are two sides to it. My specialty is sort of the rectification side. But it's interesting because Mark and I have done a lot of training, and I think we do a pretty good job of it. And when we get the questions from people after the training, 2 or 3 or 6 months later, it's never the basic questions. I think people go away from the training and pick up the basics, and people like Sean go 7 steps above the basics and are so far in front of everybody else. So the training is really good for getting people at a base level, but also taking them many steps up the rung, as like Sean. But the questions we always get are the complicated ones. We've got this really wacky thing and we don't really know how it's going to work. And Mark and I, they're like, well, this, that, whatever. and again, I keep coming back to this because I think it's a really good a good way to get information, to have risk management, to understand how your building works. And the reality is there are a lot of situations out there, and the further we push the boundaries as far as funky design, the more we get into these problem areas. And I keep coming back to this stuff of monitoring. If you've got a new funky build where you're not sure what's going to happen, put your monitors up there. In the first 12 months, you will know what's going on. Sean and I did a presentation a few weeks ago on this. And I think we're kidding ourselves if we know what every single combination, permutation, arrangement is going to do in a particular climate zone when we start pushing the boundaries and start really getting funky with the way we build buildings.
It's probably going to be a nice little segue to bring Sean back into the conversation because, if anyone follows Sean on social media, you'll see that he loves to get the hose out and he loves to spray his weather-resistive barrier down. Sean, why do you do that? Is that just for your fans on social media, or are you actually using that for, to test what you're doing?
Well, it's less stressful if it leaks when it's just the wrap, or if your bathroom fails a waterproofing test when there's no tiles. So it's like quality assurance, or like just keeping yourself out of stressful and costly situations, and just verifying what you're doing is working on site, because like we do architectural building, right? So it's never really the same. Yeah, there's similarities. We use the same products, but we might have to detail something in a certain way, a different way. We haven't done that. We're using a new window manufacturer. We want to see where these windows leak, how they manage water, things like that. So it's just it's a pretty cheap and easy verification method. You just have to allow a bit more time in your schedule. That's what we've sort of been coming to the realization of, because you're like, oh yeah, we've done a great job, and then you're like, oh, that leaks, so got to add a few more days in retaping this, or if we're going to detail that certain way, we need a flashing in here, etc.
Well, water, in my experience, and I've been in the industry for 20 odd years now, finds a way of getting in all kinds of weird and wonderful places. When you're doing that, soaking test, are you seeing water leakages in places where you didn't expect them? And what have you learned from doing that process over your years of, testing the workmanship at that stage?
Earlier on, yeah, they leaked a lot more, but as you go through it a few more times, you learn a few tricks of the trade, watch a few more Instagram reels, and sort of like take yourself to the next level of building detailing. Yeah.
And have you ever found a leak? Have you ever found a leak that you haven't been able to, stop?
No, not yet. We've
Not yet.
had to waterproof bathrooms and stuff like that. And it's just like, it takes a while to figure out where some of them are coming from.
So you test your weather resistive barriers, but you also flood test your wet areas as well?
Because that's a really expensive one when you get it wrong, right? Like, it's easy to do a bit of re-waterproofing, and it might be frustrating. You got to push the tiler back, but it's a lot worse when the client calls you because the tile's fallen off the wall.
And can I ask how you're doing that? Because in my mind, that's a really simple step to take, in that construction schedule. So how are you actually testing the waterproofing in your wet areas?
Yeah, so we just plug up the waste. Like we've got a little inflatable balloon thing. I can't remember what the place is that we bought it from, but they sell them in all different sizes. Yeah, and we plug up the waste, fill it up with water, take a measurement, and then wait 24 hours, I think it is, and then we take another measurement, and we see, like, you're going to get some loss through evaporation. But yeah, it's just taking a few measurements, and then happy days.
Pretty simple insurance policy, isn't it?
Pretty simple, yeah. And just like, I've seen the damage done from not intentionally, from water, like inside a frame, and it doesn't take long. Like, like the radiator pine just doesn't like the water at all.
I'm gonna take a bit of a sidestep here and probably throw this over to Mark, and just want to chat about air tightness in our buildings. modern ways of construction, square set plaster, caulking all our skirtings to our floors and around our windows and stuff like that, even without trying, in my opinion, our buildings are getting tighter. So what are some of the ramifications and some of the risks that we could see if we're not then managing the ventilation within the home correctly?
I think I don't think I thank Sean first of all. Just added a new line to my contract saying flood test wet areas.
I've actually taken notes too because I've seen
Thank
you
you,
do it.
Sean.
I'm like, that's definitely something that I'm
That was
looking
great. That was great. Yeah, air tightness. So I guess it's really interesting. So we've been saying, for since the 1960s, since the oil crisis, build it right, ventilate, build it tight, insulate right, and ventilate it right. So this mantra has been going for some time, and I guess those mantras did come out of our northern hemisphere locations where if a house gets cold, people die. In Australia, houses get cold and people die, but not as cold as European houses. And the other challenge we've got in many Australian houses is houses getting hot and people dying. Each time we have a heat wave, whether it's Darwin, Adelaide, or Melbourne, there's medical reports about how many people died because of hot housing. So it's not just a cold housing thing; it's also a hot housing thing. And insulation, air tightness are really important in both those things. So if you think about the old house, I'm thinking about, old part of my house in Launceston, open fireplace, et cetera, which we capped and et cetera. Those houses had 50 air changes per hour. So meaning that the air in the house changed 50 times in 1 hour. So if you were
naturally,
yep, it was just, we were just conditioning the local environment. And I guess when we got rid of our open fireplaces and those sort of things, we suddenly dropped down to the 20s, somewhere between 10 and 20 air changes per hour. But that still means every 3 minutes, the air in the house has changed. And so we're just once again heating the air and it's leaving the building. As we've got better with our, you think in the 90s we're still using green up to saw timber. We then moved to kiln dried hardwood and softwoods, and so we're having much more stable wall and floor systems. So we're getting less cracking in our plasterboard. At the same time, as you mentioned, all our jointing systems have advanced significantly in that last 20 years in terms of how we joint corners, and whether it's a ceiling wall or a floor wall or a corner junction. So all those systems have evolved significantly in that time, which has been good in terms of air tightness, but it means that we're trapping more vapor inside the building. And depending on the materials we're using, how that vapor diffusion is or isn't being supported. And we know that in 2015, that the average, I think, around Australia was about 10 to 12 air changes per hour in houses. The most recent air tightness study by CSIRO and Sean Maxwell.
Can I just interrupt for a second there, Mark? I'll just share this while you're talking. It's on my screen. Keep going.
Yep. So the most recent research by Sean Maxwell with CSIRO, was showing that in Victoria, that how a standard build volume house, which was tested, ones that were tested, were less than 7 air changes per hour. And units and apartments were less than 2. So from an air tightness perspective, that's brilliant. From a indoor air quality perspective, that's bad, because it means that there's not enough fresh air in the buildings. Why are people going to sleep? Because the CO2 levels are too high. And I guess that brings in that the mantra was about, build it tight, but ventilate right. And that's the ventilation part we have not got right in Australia yet. We might get it right by 2035. So, and whereas the ventilate right has been a critical part of the American building code, the British building code, and those since the 1980s, 90s, even the 1970s in some countries. Our ventilation was still relying on Victorian ideas of ventilation. So it's in 1800s ideas, not Victoria, Australia.
And like as in relying on the occupant to actively ventilate, is that right? Or just natural
good
ventilation
question.
through?
Yep, no, good question. So there's, I'll do a finger so I remember I've got another point to raise. But the so I guess it's really important to think about. We look at the news and we say, oh, it's going to be 20 degrees today or 24 degrees, but that's 24 degrees between 2 p.m. and 4 p.m. The rest of the day it was colder. And we know that from a thermal comfort perspective, we won't turn a heater on when it's above about 21 degrees Celsius. It's below 21 degrees Celsius, we feel cold, we turn the heater on. So if you think about that in the context of ventilation, if only between 2 and 4 was 24 degrees, so maybe between 12 and 5 was above 20 degrees. That means between 5 p.m. and midday, it was less than 20 degrees Celsius. So why would we open a window? Why would we open a window and let cold air in? So, or why would we open a window when I'm in a bunch of units and I've got noisy neighbours, or there's a guy across the road who revs his car up and it's noisy? Whatever. There's numerous reasons why we don't open windows, or never to mind that we actually go to work. We actually go to work between 7 a.m. and 7 p.m. So we're not. So the ventilation that is in the code in terms of the 5% to floor area for residential buildings is really based on the Victorian idea of, the wife was home and she opened the windows in every room of the house every day, dusted them, swept out the dust and closed them, which we haven't lived like that since probably the 1940s. But the code still has that methodology for ventilation in buildings. And I can't remember what that's what it was, the Americans. The Americans in the 1980s, they were using blower door tests way back then to improve the air tightness of buildings. And they established way back in the mid-80s that when you went below 8 air changes per hour, that you had to do other measures for managing moisture inside a building. So that's 40 years ago. They knew you had to do that. We have not brought that into our regulatory space yet.
What is this magical blower door that you talk about, Mark?
So it's a good point. So it's where we get, Sean was mentioning how we get the membranes and everything else up. So we get the build up to membranes and hopefully windows and doors installed. And then we do a pressurization test in the building. So it's a fan unit that gets fitted into a doorway. We often say you should do the front and back door because often front doors are very leaky. They have a 1/2 inch gap or even some sort of 3/4 inch gap under the front door. So doing it from 2 different locations, and you're looking at, and that creates a 50 Pascal difference. And that creates then from that you can get a measurable value for the amount of air changes inside a building. Yep, great diagram. Thank you, Clarence. And that invention, the image on the left is Freya Su. She's one of my PhD students, but she's also had a business for the last 10 years, or more than 10 years, where they've been doing blower door tests in Tasmania. And so, as Sean mentioned, you do this when the house is before you put your lining on. And I guess in Europe and America, it's even before the cladding goes on, because you get it tested to make sure everything's right before you put the next layer of the built fabric on. Because I guess we talk about interior membranes, about exterior membranes, and how we're protecting them.
Yeah, we're actually doing it on our projects before the external cladding goes on. Yeah, and then before the internal cladding goes on, because especially when you're going for, I guess, passive house certification, you want to make sure you're doing that, right on the head. So if we've made our buildings a lot more airtight now, and we're not managing ventilation, well, where's all that moisture going, and what's happening to the inside of our buildings?
So I guess a council have it's got lots of photos of moisture meter sensors. So the vapor is going into our plasterboard. It's what we call vapor diffusion. So the vapor is being adsorbed by all the materials around us, whether it's concrete, whether it's brick, whether it's only glass, and still really don't adsorb moisture. And that increases the moisture content elements. All those elements are also what we call the vapor diffuse. They allow the vapor moves through them and goes out the other side. And that's how even in a plasterboard ceiling house, the vapor is going through the ceiling into the roof space, or the vapor is going through the plasterboard wall into the insulated timber frame space, and then coming up in contact with a cold membrane or something where it might turn into condensation. Which brings us, the Clarence mentioned about the mold thing. So we know that in a poorly ventilated space, which is what a wall system is, mold grows when the relative humidity is consistently above 60%. So that's a long way before that 100% of condensation value. So, and that's where around the world, that 60% number is very important. It's why in office buildings, air conditioning is capped at 55%, because it's ensuring that the humidity never ever gets to that 60% where mold will grow in poorly ventilated spaces.
So I'm gonna again sidestep a little bit and bring Sean back into the conversation, because what we're talking about now is in existing buildings. But I know Sean builds new builds. He wraps his buildings really well. He puts, intelligent membranes on the inside of his buildings, but he's also introducing, from what I understand, heat recovery ventilation systems, which is obviously managing our condensation within the home and bringing fresh air into the building. But Sean, I want to know, during construction, managing water is really tricky. Now, as we are seeing such a massive uptake in education when it comes to the risks around mold, our timbers getting wet. Zara does a great job of, has done a great job of educating a lot of us in the risks of mold. And the risks of mold, as we're locking that up into like a wall assembly on the inside, what are some of the things that you do when how are you managing that during construction when your frames get wet? And then if they do get wet, what are you doing before you put plaster on?
The biggest thing to say is they do get wet. Like, people don't talk about that enough. When you're building in the winter, your frames are going to get wet. So
I think when you're building in Tasmania, your frames are going to get, regardless of whether it's winter, spring, summer.
Yeah. So it is giving them enough time to dry and encouraging drying before we go and put any internal linings on or install any insulation. So that is the trigger point. We need to get these frames back down to under 14%, I think the number is. So business as usual, things get satched. We do all the external membranes. We can put the roof on and everything like that and make the building weather tight. And then we start the drying in process. So in the past, we've done it with like diesel heaters and fans. We've found that the air moving fans have been more effective than the diesel heaters. And the diesel heaters aren't that great when the building's locked up nice and airtight and you're pumping fumes in. We're on the outside, no one's on the inside, but gets a bit stinky. Another method could be like those commercial grade dehumidifiers. They're quite expensive. We've gone and bought ourselves like a suite of really big air moving fans. That was like half the cost of getting a dehumidifier in for the week. So we've just sort of added that to our toolkit. But yeah, encouraging drying and airflow, and then just checking it with a moisture meter to see what that moisture content is before we go and put things in the building that are going to stop drying, like insulation and internal linings.
What about if you do see mold on that? We were talking about before, I think Clarence mentioned that hardwood timbers are less susceptible. They manage the mold a bit better than, say, the softer timbers that we're typically framing with. If you do see mold, and I mean we're all builders and chippies here, we've all seen it on the bottom plates because it's sitting hard
100%.
onto the ground. So what can we do? What are some of the things we can do to manage that risk?
Yeah, mold is 100% there. Like, if you think it's not, you're kidding yourself. Like, some of the timber rocks up in the packs moldy. We usually pull that out, chop it up. But yeah, so the last job that we did, we had quite a fair bit of mold in the subfloor. Got really wet through the winter month, like heaps of rain through the winter months. And we just get contractors in to like, they spray and kill the mold, and then I just put myself in a suit and then went and like physically got rid of it with a drill and a brush. But yeah, you need to do some sort of treatment, and then there's a few methods of like the HEPA-vac sandwich where it's like a wipe and then a vac with a HEPA-vac and then another wipe. There's a couple of different methods that people can look into. We just get the guys in to do it, but it is just more like, it's another thing. There's more time in your schedule, especially when we're going through the winter months. We're like, all right, well, plaster's not realistically, maybe we need a 3 to 4 week window before the guys come to insulate. I think that's how long it took on our last project. It was about 3 to 4 weeks to dry the house back out. Luckily, it was quite a large scale project. Like, we could move on to a lot of other things, but yeah, it's something you need to consider. Yeah,
I'm gonna throw something here because I've been thinking about this for a while, and I've seen it on a Grand Designs episode in New Zealand. Packers underneath the bottom plate.
Yeah, skate plates. I think that is an answer, but there is implications to that. Like I reckon there'd be some structural implications to that. You definitely, before you go do anything like that, you definitely want to have a
Engineer.
chat to your engineer and say that is something that we're considering. But yeah, you don't want to just go doing that and then not talking to your engineer about it, because it may
Oh,
change some tie down or hold down requirements. But like that is creating the gap, right? So you're not going to get the 20 mil of rain and the 10 mil of water sitting on your slab, soaking into the bottom of the bottom plate. You're going to have that, like that drainage is king, right? So you're going to have that drainage. So I think it's a really good idea. I haven't done it yet. I'm interested in doing it.
I can't wait for you to try it and then blog about it on your Instagram page. I'd
I'll
love to
tell.
see how it goes.
Yeah, I'll tell you all the like things that you don't think about, and then what you can do next time.
I love it. Clarence has got his hand raised. I was about to throw it to him, but Clarence.
Oh no, and as I mentioned before, that there are a lot of areas in this that are still evolving, and I think this issue of mould on frames when they're constructed is absolutely one of those areas that people don't completely have their heads around. And when was the last time you went past a frame and truss yard and saw all the frames and trusses out in the yard covered over? They might be sitting there for a month before they even get to use. So there is a huge issue around that, and Mark can probably talk from the hydrothermal modelling point of view. But again, there are areas where we're evolving and we don't know all the answers. However, what Sean said, I think that the single worst thing you can do is wrap your building up when it's wet. I don't know if there's a 14% number formally written anywhere, but that sounds pretty right to me. But this idea of whatever you do, don't wrap your building up when it's wringing wet. That's probably the single biggest takeaway until we have further knowledge or better practice, if you like.
You touched on hydrothermal modelling. I might throw this to Mark. What is hydrothermal modelling? You're on mute, Mark.
Yeah, I'm just
There you go.
I'm trying to. I was enjoying the other discussion again. Yes. So hydrothermal modelling is where we, I was mentioning before, how every single material, or most materials, are what we call vapor diffuse. So we have a rate at which the vapor can move through a material. Clarence has probably got a movie somewhere he can show, one of my movies. And so we know each material's properties in terms of how vapor moves through it. We know each material's properties in terms of what we call conduction, which is how heat moves through material. So hydro, water, thermal, heat. So it's about understanding the flow of heat and moisture through a building. And then we have climate data in terms of what's happening outside the building. And next slide up, probably, Clarence. Yeah. And so this image that Clarence is showing there, my mouse works. This red section is the temperature through the wall system. So on the right hand side is inside the wall. On the left hand side is outside the wall. The green area is humidity. That's the moisture moving through the wall. Once again, the right hand side is the inside, and the left hand side is the outside. And the blue line at the bottom is actually what we call moisture accumulation. So naturally, we can see that there's a timber cladding with paint. And there's quite a lot of moisture in there because that's natural, moisture from rain events on the cladding. But we can also see right at the bottom, there's a blue line at the bottom where there's a bump of moisture just inside the membrane. What we can also see is how, coming back to that 60% relative humidity value I was mentioning before, we can see in this wall system how most of the time it's above 60%. So we could say if I went and looked at this house after 5 to 10 years, I would see significant mold growth on that last third or the outside third of all the pine studs. And so around the world, we've been using hydrothermal modelling for 30 years. 1990s was when the first softwares were being tinkered with and published. So they've been using, for 30 years, they've been using this software to inform building envelopes at a regulatory level and at an individual project level, so that we understand what's happening, and then we can design the wall system at this point rather than after it's been built to actually manage the vapor and to reduce that risk of moisture accumulation and or mold growth in the wall system.
I realised that I was on mute then. So I hear woofy a lot, right? Because I kind of operate in this sort of high performance and passive house space. But what I'm hearing now is like this hydrothermal analysis or a woofy analysis probably needs to apply to more than just high performance and passive house builds, where we're probably want to be running these tests, or you can run these tests on just your more standard building stock. Is that right?
Definitively, I guess I can say with some confidence, I should say with some confidence, I can say with some research confidence that if you build a wall to the code as it stands as of 2019 or 2022, there's a very high chance that in most parts of Australia that you'll have mold, and which is a concern. And I guess this is that reinforcing is that big. I was mentioning how these regulations in other countries were coming into place since the 1970s. Our first bit was in 2019. So we're a bit behind.
And I guess this is quite topical as we sit here on the 27th of August in 2025, because we've all just learned that they're, in the government's wisdom, they're freezing any changes to the NCC. And I know I'm going to try not to throw anybody under the bus here, but what are some of the things that we could see as a result of these code freezes?
I guess we mentioned before about ventilation. So there's issues about air quality inside houses. We've got mold growth inside houses, mold growth inside walls. I think if people are just doing a basic cookie cutter home, for better words, with the 23-degree pitch and ventilated roof space, I think roof spaces will be quite safe. One of the big problems we identified for the Victorian government and the Tasmanian government is that, and similar trends have been found in New Zealand, Canada, and Belgium, is that brick or masonry buildings, so the brick veneer in our terms, they're increasingly problematic. Yet they're about 60 to 70% of our builds in Australia. And
can you probably explain why that's the case?
That's fine. Yeah. So and that's a really good question. So what it appears to be is that if I think about a timber cladding or a cement sheet cladding, there's very little capacity to hold moisture. So we think, on the north side of the house that gets sun, it's happy, ventilation's working, all those sort of things. On the east and west, the east, you get a few morning hours of sunshine, and that's really helping in terms of warming the wall up. As long as it's just once again coming, these aren't code compliant walls, these are walls with a ventilated cavity. So we've got the wall system with drying potential. The west wall is the next highest risk because it's cold until after midday. So that whatever's in that wall is cold until after midday when the sun comes around. And then our problematic wall is always the south wall, where aside from in the summer months, it's always in the shade. So if you think about a clay brick, it's absorbing moisture, it rains, gets moisture, and with very little capacity to have a drying potential, aside from what air is moving around the building. So that's a cold, wet object that's 40 mils from the next layer of the building. So that next layer is being kept cool because of the wet clay brick. Yeah.
And there's probably a false sense of security in, cladding our homes in brick or masonry, thinking that, water's not going to get through that. But from what you're saying now, there's probably a greater risk of moisture being trapped. Am I saying, the brick's going to hold moisture and then it's potentially going to drive back into the building?
Correct. You've got what we call the inward vapor driver. Yeah, inward vapor driver. And so it's other countries have been exploring, do they make cavities 100 mils, so increasing vapor rate? We've tried that ourselves in hydrothermal simulation. What we've tentatively, and we're still working on it, the addition of the interior membrane helps a little bit, but not enough. A very vapor open exterior membrane, but also looking at having to add insulation to the outside of the frame. So we're trying to keep the timber warm. How do we keep that timber above, keep it warm, and at the same time very vapor open, vapor permeable, so we're helping the vapor to just leave whenever it can.
It's 5:54, and we could chat for hours, I would imagine. I am going to ask each of you one question, and we'll try and keep our answers quite succinct. And I'm going to start with Sean. If you could change one thing in the NCC, what would it be?
That is a good one. I'd say more mandatory inspections. That's going to piss a whole lot of people off. But you just need to, there needs to be more verification of what's going on site. Yeah, it's just not enough, and people can just get away with too much because there's not not enough of those mandatory inspections. Yeah, that would be that's going to piss everyone off. The answer there.
I actually recorded a podcast with Macalister today and a construction lawyer, and we were saying that waterproofing should be a mandatory inspection. And I know everyone's going to throw their hands up in the air and say it's going to be too expensive, but why not have a self-assessment portal where you're taking pictures and uploading it into, like, directly to the VBA or whatever they're called now, that you're actually verifying it? You know, just even that simple step of actually taking a picture of it and, you know, self-proving that it's been done correctly. I agree with you, Clarence. I'm keen to hear your what's the biggest shortfall in the current one, or what's a change that you would like to see? You're on mute, Clarence.
Look, I think there's a lot of politics around the NCC, and look, I think it's overall an okay document. I'm not going to say it's exceptional, but I think the single biggest challenge is going to be around ventilation. Now, Mark knows a lot more about this than me. Correct me if I'm wrong. That the assumed air change rate in a building is 10 air changes an hour at 50 pascals. If you have it less than 5 air changes an hour, you need to have mechanical ventilation from a health and condensation mold point of view. And the number of buildings that are creeping down into that danger zone of ventilation and not being addressed from a ventilation point of view is increasing every day. And not just for us as builders, but the health outcomes, and this is what the health people are saying, not the builders, the health costs are phenomenal. We're talking billions, $10 billion a year, they're saying. And I think the biggest challenge for NCC is going to be ventilation, and the biggest thing for us as builders, the further we go down the pointy end of energy efficient and high performance homes, is ventilation.
Yep, I agree. Mark, what about you?
That's one thing. Actually, I'm going to say we need to do a shift in the code from this R value, or whatever it might be, to a minimum and maximum temperature within buildings. And numeric numbers, that if a house goes below a certain number, it's not compliant. If it goes above a certain number, it's not compliant. Coming back to Clarence's comment, the publications from the medical space regarding deaths and illness from cold housing and deaths and sickness from cold housing in Australia. The stuff out of Victoria and South Australia is quite frightening in terms of cold housing in South Australia and the number of deaths. I never thought South Australia was that cold. So I think we need to do a shift to more of a performance requirement for buildings for human health.
So there is some good news out there, people. Now, I know that the NCC is, apparently frozen, and, we're all sort of throwing our hands up in the air and, shaking our heads as to, that this shouldn't be the case. But we actually have a choice of how we build the homes, right? All the technologies exist now. There is this wonderful organization called Sustainable Builders Alliance. I don't know if you've heard of them before. We've got a website, www.thesba.com. It has a ton of free information on there. There's a roadmap to carbon zero. There's a bunch of engaged builders on there. Talk to guys like Sean, Clarence, or Mark. Like, the information exists as we stand here right now to build better homes. You don't have to rely on the code to tell us how we need to build a home. Like, this is actually a choice. Now, I haven't been able to get to any of the questions, and I am conscious of time. I am going to throw out to anyone listening today that if you did want your questions answered, jump onto our social media page and throw a question in there. I'll pull them all out, and I'll pop them into an email, and I might send them out to Mark, Sean, and Clarence and see if we can get some answers. And I'll even throw them to, we've got a huge knowledge base in Sustainable Builders Alliance with obviously Jeremy and Jess and the Michaels and Brian and stuff like that. So we can answer some of them. I know that this topic is really relevant to a lot of people out there now, but I am going to wrap it up, and I just want to say a massive thank you to Mark, Clarence, and Sean for taking the time today to share all your knowledge. And I can't help but feel we've just scratched the surface of this big topic, because it's huge. We're never going to solve it in an hour. This webinar is going to sit on our website for free. You can access it whenever. We do have a YouTube channel. Be sure to jump on and look at all our past webinars. Don't forget that we also have a podcast, the Sustainable Builders Yak. I believe that Jeremy McLeod from Breathe Architecture was on there recently chatting with Brian and Simon. You can listen to them on Spotify. You can also get access to them through our website. Next month's webinar, we are joined by one of the OGs of sustainability and founding director of Sustainable Builders Alliance, and that is Mr. Jeremy Spencer. And we're going to learn more about the difference between net zero and monthly net zero, and how to design and build homes that are affordable to run and resilient and ready for the future. I'll get some marketing out for the webinar over the next couple of weeks. And I'm going to do a really quick plug. SBA is now a member organisation, and for a small fee, you can jump on and become a member to show your support for the work that we're doing. You can stand out in our Sustainable Builders directory, showcase your credibility, access real work learning, and you can save a bunch of cash on member-only deals. That's it from us. Mark, Sean and Mark, thank you so much for coming on today. And I do apologise for the questions that I didn't get to. I have absolutely no doubt that I'm going to chat with each of you on another webinar in the not too distant future. But again, thank you so much for joining us today. We'll catch you later.